nastavak SUZI predavanja, odnosno predavanja koje organizuje Srpsko udruženje za zemljopisno inženjerstvo. Danas imamo čast i prilike u slušnom predavanje iz čeličnih konstrukcija, pa onda u oblasti zemljopisno inženjerstva i profesor Primož Može. Ja ću pročitati kratko biografiju, pre toga samo da kažem o Srpskom udruženju za zemljopisno inženjerstvo. To je tehničko nevladino udruženje koje okuplja građevinske inženjere, arhitekte, nevladine organizacije, druge i vladine sektore za vanredne situacije, geologe, seizmologe, svi koji su zainteresovani za oblast zemljopisnog inženjerstva, pa i vi. Hvala vam što ste ovdje, nadam se da dobijate na vreme informacije od Srpskog udruženja za zemljopisno inženjerstvo. Od skoro smo postali članovi Evropske asocijacije za zemljopisno inženjerstvo, od početka osnivanja malo ne smo i članovi Međunarodne svetske organizacije za zemljopisno inženjerstvo. Tako da možete svakako na sajtu se informisati o svim informacijama i postati članovi. Ono što je korisno i bitno jeste da sva predavanja snimamo i postavljamo na YouTube, tako da možete uvijek na miru uz kaficu i detalje proanalizirati. A sva predavanja naši predavači nam daju u PDF-u i okačimo ih na website, tako da samo SUZI članovi mogu da pristupe tim PDF materijama. S obzirom da će predavanje biti na engleskom, ja ću sad prebaciti na engleski da pročitam biografiju i da predstavim našeg današnjeg predavača. So, Associate Professor Primož Može is Professor of Steel and Composite Structures at the Faculty of Civil and Geodetic Engineering, University of Ljubljana, where he holds several positions. His main research areas include joints in steel structures, high-strength steel, and stability of plated structures. He was a member of the project team responsible for developing second-generation Eurocode for design of joints in steel structures, and is an active member of CEN-TC 250, Working Group 8, and ECSS-TC 10. He has authored several articles in leading international journals, served as editor of a special issue on joints and connections with fasteners for resilient steel structures for the Journal of Constructional Steel Research, and he is editor-in-chief of the Slovenian journal Gradbeni Vestnik. He was responsible for Slovenian coordination of several European national projects, and he is also president of the Slovenian Association of Structural Engineers and vice president of the Slovenian Mirror Group of CEN and group of ECC-TC10. We have a pleasure. Thank you for taking time to visit us in Belgrade and take time for giving us a lecture with the title Design of Steel Frames for Earthquake Resistance. Primož, the floor is yours.
Marko, thank you very much for this kind of introduction. My name is Primož Može, and every time I come in Serbia, it's a nice story with this surname of mine. Today at the reception, when I checked out, the guy at the reception asked me, okay, možete li kazati vaše prezime? Ja kažem, može. On me gleda i pita me ponovno, molim, kažete mi vaše prezime? Kažem, može. Onda se gledamo, a onda me pita na engleskom. Kažem, može, to je moje prezime. Tako da. It's very nice to be here. Today I will talk about the design of steel frames for earthquake resistance. It's a very wide topic, and hopefully we will come more or less to the end. So we will start with the basic principles, then go with a brief overlook of analysis and behavior factors. So this I will try to go through this very quickly. We will also discuss about second-order effects, and then we will put more time into the methods of energy dissipation and about the material design concepts, and then about general ductility and strength requirements, and then we will come to the frames. First with moment-resisting frames, and then design rules for concentrically braced frames and eccentrically braced frames. So if we start with the basic principle, I will talk a lot about capacity design, ductility, and overstrength. So to clear out those terms, we can make an example of a chain. And if you imagine a chain, the particles that are all of the same material, all of the same nominal material, but every particle has its own yield stress that we don't know how much it is. We say, okay, the material is N235, and we would like to design this member to be a dissipative ductile member so that the failure will initiate in this particle, and all the other members would stay in elastic area. As engineers, we operate with nominal strength and design strength, so we don't know what is the actual material strength. And for this reason, we must take into account the overstrength factor. So we say, okay, we assume that this red particle has an actual yield stress of, let's say, 295 megapascals. And for the black particles, we say, okay, this should stay inelastic. They have the minimum value of yield stress, okay, let's say 230. So, and we know that the force, the resistance of the non-ductile members, this one, should be higher than the actual member. So, we use this overstrength factor that is 1.3, that is the ratio between the expected value and the nominal value of strength, and we use this overstrength factor to increase the resistance to the strength of the dissipate member, and we use this force to design the non-dissipative member. And this is called capacity design. So we design the member which will fail, and all other members we design with some overstrength to be safe to be in elastic zone. And this is the basis of the capacity design that is also used in the Eurocode standard. So if we put this into the frame structure, so the frame structure is statically indeterminate many times, and it's quite logical that we should design the weakest part of the frame should be edges of the beams. So in these areas, plastic hinges can form, and the structure will still stay stable until all the possible plastic hinges occur. Then the frame will lose stability. So we design the edges of the beam where the energy seismic energy should dissipate on the forces that we get from our analysis, and the columns should be designed with sufficient strength not to fail. So the columns should be designed with overstrength factor. So this concept is called weak beams, strong columns, and this is the basis of the design of steel frames. So if we look on the analysis, we know that seismic motion is movement on the ground, and the structure will make a response on this seismic movement with some inertia forces that mainly depend on the period of the structure. So we use this rule of equality of displacement. So we say, okay, if the structure will have elastic response, will have more or less the same displacement as if the structure has nonlinear response that we take into account the ductility of the structure. So, but this means that we can decrease seismic forces, so we can use much reduced seismic forces to design our building. But on the other hand, if we decrease these forces, we must have a certain amount of ductility to reach the desired displacement, the demand that the earthquake has. So it's always a question whether to make some force-based design or displacement-based design. Force-based design is very natural for engineers. It's very easy to understand, while displacement-based design it's more difficult, more knowledge is needed, and so we usually use force-based design with the reduction of seismic action by this behavior factor that is called Q. So this factor tells the ability of the structure to dissipate energy. Eurocode allows many kinds of analysis for seismic response. So we can divide them into linear analysis and nonlinear analysis, and to linear analysis we use response spectra with elastic spectra and reduced design spectra with this red curve where we reduce the seismic forces, and then we can make some equivalent lateral force method, which is a very basic method, but in Slovenia we use mostly this modal response spectrum analysis, where you calculate the period, and then automatically the forces on the structures are calculated, and when you get some internal forces, then you can start with the design. Then we have some nonlinear analysis with the pushover analysis. This is one of the basic analysis. It's a static analysis. With this pushover analysis, we can calculate the behavior factors. This is the ability of the structure to develop ductility. And there is another analysis, time history analysis, which is the most demanding analysis that requires most knowledge, and it's rarely used, or it's used for some more important structures, let's say for some hospitals or nuclear power plants or so. Okay, the Eurocode also tells us what are the conditions to use whether implant, whether we can use a planar model, numerical model, or we should use a spatial model. This depends on the regularity of the structure in plant and in elevation. And also whether we can use the most simple method, so this is the forced method, or we should use modal analysis. And if the structure is irregular in elevation, then we must reduce the behavior factor for 20%. So the in-plane regularity is this kind of structure that both dimensions in plane are more or less the same. If one dimension is much smaller than the other, or we have some L or U configuration, these are non-regular structures. And in elevation, the regular structure is if the stiffness of the structure is decreasing from bottom to top. But if you have these large steps in the stiffness, in decrease of stiffness, or if the stiffness increases toward the top, then this is the irregular structure that more attention is in. Okay, so this is the response spectrum that is based on the return period of 475 years. The spectrum we show is this is type 1 spectrum, for ground type A, for PGA, P-ground acceleration of 0.25 g. Here we see the elastic spectrum with the blue curve and the reduced spectrum. So the steel structures can have really large ductility, so we can reduce the seismic, the elastic response spectrum by factor of 8. This is the maximum allowed. If you talk about the behavior factor for steel structure is has two parts. So one is the reference value, and the other is the overstrength factor. This is alpha u over alpha 1. So alpha u presents let's say the multiplier of the forces that will cause the collapse of the building or development of full plastic mechanism, while the alpha 1 factor is the multiplier of the forces that will develop the burst plastic hinge. So you can see the typical steel structure has linear response, this is elastic range, and when the first plastic hinge occurs, the stiffness starts to decrease, and this is because of the development of plastic hinges all over the structure. The stiffness decreases, and then reach this maximum resistance. The second generation of Eurocode has a little bit different approach. It's more, let's say, more accurate approach. So the behavior factor consists of three factors. The first one is QS. This is a component accounting for overstrength due to some other sources. The QR is actually this alpha U over alpha 1, which we just explained. And the QD is, let's say, this reference factor for the structure, that depends on the structural type and on the ductility class. So this is quite some difference also in these factors. So if you go back to the first generation of Eurocode, the Eurocode tells us, gives us the guidance on how to select the Q factor. So the first part is this overstrength factor that we see depends on how many bays the steel frame has and how many floors. So one bay, one floor, the factor is 1.1, one bay, several floors, 1.2, and multi-bay, multi-floor, 1.3. Then when we talk about concentric bracing with tension diagonals, these are the schemes of the structural system. So the centric braces, the main point is that the braces will intersect with the column or the beam, and with the other brace, the braces can be in two separate brace or in this configuration. But the main point is that in these concentric brace structures, the X bracing, only tension diagonal carries the load, while the compression one buckles. And then we have frames with concentrically bracing. In this configuration, both diagonals must carry the load, because once if the seismic forces act from left to right, then these left braces are in tension and the right one are in compression. And when the compression diagonal buckles, then it's end of the story. So the frame goes towards the collapse. Then also frames with eccentric bracing are also structures that can dissipate a lot of energy. In this case, we have some eccentricity. The braces do not connect in the same node, but they form a kind of link that the Eurocode calls seismic link. So this seismic link can be positioned in the middle or towards the end of the beam, or two seismic links, or a vertical position of a seismic link. The overstrength factor 1.2 can be assumed with eccentric braces. Then we have also some other kinds of structures that we will not talk about today. So this is the inverted pendulum structures, the structures with concrete holes, of course, where the concrete takes all the seismic load. So these are basically the concrete structures. Then the concrete part is designed for seismicity. Then we have dual frames, so the moment resisting frame plus concentric bracing, where we take only one Q value, one behavior factor. Then some moment resisting frames combined with infills, so the infill is very important. If the infill is connected with the structure, it makes a composite structure, so we designed it as a composite structure. But in case we want to use a moment resisting frame, the infills must be always spaced away from the steel structure. So we usually put some thermal insulation, some soft insulation that we allow the steel frame to move independently of the infill. While this K bracing, that is used many times, especially in industrial halls or also in buildings. This is not allowed in seismic areas. So to get the feeling about the Q factors, these are the two ductility classes that we will discuss a little bit later. Medium ductility class and high ductility class. Eurocode gives us two ductility classes, DCM and DCH, but for steel structures only rules for DCH for high ductility class are given. So I will focus mostly for the high ductility class. And we can see that moment resisting frames have very high ductility, 5 times alpha U times alpha 1. So 5 times 1.3 makes it 6.5. So this is the behavior factor for steel frames. And the maximum value of alpha U over alpha 1 is 1.6. So times 5 times 1.6 is 8. So the maximum behavior factor for steel structure for moment resisting frame is 8. Frame with concentric bracing have 4, with diagonal bracing, with wheel bracing only 2.5. Here is also the difference in the second generation of Eurocode that increases the Q factor for wheel bracing. I will say later why. Then frame with eccentric bracing, 5 times 1.2 is these overstrength factors, make it 6. So frames with eccentric bracing have also a big ductility, big ability to dissipate seismic energy. The second order effect can be directly considered only in nonlinear static analysis. This is pushover analysis or dynamic analysis. If we use the modal analysis or equivalent force analysis, we must take P delta effect into account by theta factor, by coefficient theta. Theta is basically 1 over alpha critical. So alpha critical is elastic critical factor. So the theta value is calculated that we compare to overturning moment. One overturning moment is the P total. So these are the total vertical, the total gravity load at and above the story due to the masses. And DC is the interstory drift. So this is one overturning moment, and we compare this overturning moment with the overturning moment that is caused by horizontal forces. So this is the total shear in the seismic design situation. And will be multiplied with this story height. So this is the other overturning moment. And what is important to point out that this DC, the interstory drift, is calculated. These are non-reduced displacement. So these are the displacement that elastic structure would have. So when we are our analysis, we do our analysis with reduced seismic forces. So if we take the displacement from our analysis, we must multiply it by the behavior factor Q. So if the theta is below 0.1, then the P delta effect can be neglected. Earlier I said that theta is 1 over alpha critical. So you know that for steel structures we must take into account the P delta effect if the alpha critical is below 10. So this is very similar, only the inverse numbers. So if the theta is between 0.1 and 0.2, the P delta effect must be taken into account approximately by K delta factor. It is calculated as shown here. If it's between 0.2 and 0.3, we must do pushover analysis, more accurate analysis. And theta above 0.3 is not allowed. This is one of the conditions that is very critical when we design moment resistant frame. because it was introduced a little bit wrong in the first generation of Eurocode, because this theta value actually presents the second stiffness on these displacements, on this, let's say, displacement that developed near collapse stage. But the second generation of Eurocode defines the theta a little bit different. So basically everything is the same. This dr SD is the displacement at a significant damage. So it's basically calculated in the same way. So the displacements from our analysis are multiplied by Q factor. But here then we divide this with QS and QR. So we are the theta factor then are a little bit lower, so this criteria is not so strict anymore as it was before. Okay, now we come to the very important part, the dissipation of energy in steel. So here you see hysteresis of steel strain. So you can see that the steel can have really nice hysteretic, closed hysteretic loops. It's able to dissipate a lot of energy. But the steel fiber, it's not steel structure. Steel structure has elements where some of the cross-section is in compression. The compression is related to stability, to local stability. Then we have joints where we have very high concentration of stresses and strains. So and all these things can reduce ductility. So when we talk about dissipation of energy, the three basic methods to dissipate energy are in bending, in shear, or in tension. So in bending we create plastic hinges in bending. In shear we can dissipate energy in these seismic links, where we dissipate energy in the web of this link. And in tension, we dissipate energy in concentric bracings in diagonals. So how does this work? Excuse me. So here you can see one test from our laboratory. This is the scheme of the test. The column in this case was composite, but it doesn't matter because the plastic hinge occurred here. And you can see here the failure. So when the plastic hinge occurred, you can see here the local backing of the flanges. And you can see here that this cross-section was able to dissipate a lot of energy. There are a lot of cycles with closed loops. But sooner or later, this degradation or softening starts. And then sooner or later, we experience the fracture of material. These are just to show how this occurs. So the pin is loaded upwards and downwards. So you can see here the plastic hinge occurs. So this is the pane that fractures when with a high strain. So you can see large plastic strain. And now we will see the degradation. And this degradation is related to the local backing of the flanges. So the flanges are in compression. The one is in tension, the other is in compression. And when we are in this plastic region, we don't have any material stiffness, and sooner or later the flange buckles. So we come to the first rule that we must always obey, that if we want to dissipate energy in bending, the cross-section should be class 1. And then the fracture occurs when we have this, plastic strains due to axial compression and tension, and then we have strains from bending. So the strains here local are really high, and sooner or later fracture occurs. So the other option is to dissipate the energy in shear, in these shear links, seismic links. So if you dissipate in shear, the shear is taken by the web, so the web needs some local stiffeners to prevent buckling, local buckling of the web. Because you know shear is always if you rotate, the stress field is rotated, so we have one tension diagonal and the other is in compression, and the one that is in compression wants to buckle the web. So we need these stiffeners. Here are some applications. So these are some tests of industrial hole that was done in Italy. So this is for strengthening of when we want to strengthen some existing structure. We can use these eccentric braces that is put vertical, and this is the test in Ispra in Italy that was a full-scale structure. Here you see a seismic link that could be taken out and replaced after the earthquake. And you can see here all the strain, the plastic strain occurred here in the web. These are some tests to show the behavior. So if this is a short element tested in shear, and we can see that buckles, here are some buckling, and due to this buckling, we have this pinching effect in the hysteresis in these loops. While if there are stiffeners present, the pinching effect is not so pronounced. And the third way of this classical dissipation energy is in tension diagonal. So this is very complicated behavior because the diagonal is once it's in tension, and when the loading is from opposite direction, the diagonal goes into the compression and it buckles. So here is this is the one diagonal that is in the test. You see it's here, it's buckled. And this is the cyclic behavior. So this is tension side and this is compression side. And here we can see this delta that is shown on this horizontal axis. And what is the behavior of the diagonal? First, if you go into tension, the diagonal carries some load, and then it reaches the point when it wants to buckle. Diagonal buckles, so we get a big displacement. We are shortening the diagonal and pushing it, and the diagonal cannot carry load, you can see here. And then at this point B, we turn the loading, we go into the compression, and first what we want to do is straighten diagonal. It's buckled and we want to straighten it, and when we are straightening, the stiffness is not that high. And when the diagonal is straight, the stiffness increases. And then here at F point, we go into the yielding of the diagonal, and the diagonal starts to dissipate energy, and in this point G, we turn the loading back to the compression. And if you look here at the cycles, we can see that this peak, this is the first cycle in compression. The first cycle, the diagonal can still carry compression load. While in the second cycle, the diagonal has been is yielding in tension, is imperfect, and in the second other cycle cannot carry as much compression load as in the first cycle. So this is very complex behavior of this compression bracing. And here you will see some compression bracing. This is the only one half. So it's like this, but if you cut it here, you can see this bracing. This was tested. Here the braces were almost slender. It was class 3, but on the border with class 4. And the seismic load was the accelerogram which was with the 0.25 G. And here you could see the buckling of the brace. So this was quite small earthquake. If we go to the next, then we increase the PGA to 0.44. The same brace is not repaired. What is interesting to observe is this corner. Here you can see this detail. The brace always buckles out of plane, because out of plane is more slender than in plane. So we have to design this detail very carefully, not to have failure in this gusset plane. So you can see here the brace is buckling and then going to tension again, dissipating energy and then buckling. But when we tension it, when the brace dissipates energy, it elongates. So in the second cycle, it's already elongated. So when the earthquake stops, both braces are buckled. And this is the last test. When fracture occurred at 0.5 G, you will see a very sudden failure because of this class 3 on the border with class 4. You will see a fracture here. So you can see really huge buckling of the brace. And this is the end of the story. There are also other options to dissipate energy. Seismic isolation is more and more used also in Italy, not only in Japan. In Italy they use it quite a lot. And there are dampers with check memory alloys, buckling restraint braces. So these are the braces that dissipate energy with this inner core, and this outer core has a function that diagonal does not buckle. Then these are friction dampers, so connections with friction dampers. Here is the friction damper. These are the structures without any damage, so all the energy is dissipated with friction. Tuned mass dampers, hysteretic dampers, and many other ways that we can dissipate energy. So if we go to the material now, all material that is in Eurocode Part 1.1 can be used for dissipating energy, but it's recommended to use S235, S275, and S355. But the lower the grade, the better is for dissipating energy. Now we come to these capacity rules and overstrengths. So we design our structures with nominal and design strengths. Since the gamma M0 is 1 for steel structure, so the nominal value is also the guaranteed lower bound. But we know that our zone where we dissipate energy will not have the nominal value of strength, but you have something else. And let's say you have some average value. So we must take account, when we design the non-dissipated members, we must take into account that the dissipated zone will yield at higher, let's say, plastic moment, at higher yield stress than nominal stress. So the expected yield stress in the dissipation zone is calculated as gamma overstrength, which is 1.25. 1.1, which takes into account the strain hardening effect of steel and the nominal value of steel that we are using. And we will use always these two factors when we will design the non-dissipative members. Eurocode, the second generation Eurocode, also changes these things, because they figure out with several European projects that these values were too low. So instead of gamma overstrength, now it's called omega RM. These are its randomness material. So this factor takes into account the variability of steel yield strength. So the same as gamma OB. And it's different, it depends on the steel grade. The higher the grade, the lower the factor, but you see that it's very high factor for S235. It's 1.42. And then we have omega SH, so omega strain hardening. This takes into account the strain hardening. and it depends on the structural type. So you can see that it can be 1.2, 1.1, or in some cases in shear also 1.8, because in shear the strength hardness is very high, so these factors are very, very high. Currently, a version of Eurocode does not give any additional requirements for toughness. You can use JR toughness, but in Slovenian annex we are saying that you must use at least subgrade of J2. And also this is something that is changing in the second version of Eurocode, that higher toughness is required, J2 or in some cases even higher. So now if we go to design concepts, so Eurocode gives two design concepts, so whether low dissipative structure behavior or dissipative structure behavior, so DCL, DCM, DCH. I know probably you're familiar with this, so I will not spend a lot of words on this. So as I said, for steel, Eurocode gives only recommendation for DCH. So there are no additional rules for DCM. So when we are designing, we are always using ductility class high. So the ductility class, low ductility class, all cross section can be used, and the design can be done with Eurocode 3. Eurocode 8 does not need to be taken into account. In Slovenia, we don't have any areas where we could use this approach. We always must design with dissipative concept. But as soon as we get to DCM or DCH, we must obey the rules, the additional rules that are given in Chapter 6 of Eurocode 8. Because the design goes like this. We assume some behavior factor, but to achieve this behavior factor, we must obey the rules, the additional rules that are given in this Chapter 6. If we fulfill all these requirements, then the structure has this behavior factor that was initially prescribed. Otherwise, we can make a big mistake. Also, the second version of Eurocode gives more information on when at what seismic action index we can use DC1, DC2, and DC3. You can see Eurocode 2, second generation, defines different classes of ductility classes because the definition is a little bit different, so the naming was also changed. Before it was DCL, DCM, DCH, and it was changed to 1, 2, 3 because of different meaning. But more or less the DC3 is more or less the same as DCH. And DC1, let's say, that has more or less, it's not the same, but it's very similar to DCL. So I will not go through the definition of these classes, DC1, DC2, DC3. So basically DC1, only the overstrength capacity is taken into account. With DC2, we take into account only local overstrength and local deformation capacity, while DC3 we have whole hierarchy of rules. So the ability of structure to form the global plastic mechanism at significant damage. Okay, now we come to more to the general ductility and strength requirements. So we will speak about local and global ductility. Local ductility is ensured at the level of cross section, while when I talk about global ductility, it's ensured at the level of the whole structure. So local ductility is related to joints and cross sections, while global ductility to form the plastic mechanism of the whole structure. So we see that, as I said, I will speak about DCH. So the requirement of DCH is cross section 1. We saw that on the test before. Why is that? To postpone local buckling in the plastic region as late as possible. then, of course, we must have ductile material, but all the material that Eurocode gives are ductile. And all the global instabilities must be prevented. This is the basic thing that if you want to form the plastic mechanism, we want to prevent the buckling, lateral torsion buckling, and so on. In tension, it's very important that we don't have any weak cross section. So the yielding must occur on the whole length of the diagonal, because then the strains on the whole the elongation of the diagonal, it's delta L. So if we spread this delta L in strain over this L1, so we have much lower strain than if all the strain happens in a very short length. So this also means that all the connections must be sufficiently strong. We must not drill holes into the cross section, but we must first strengthen the cross section and then drill holes through it. Otherwise, we will have weak cross section. We will have this case. For seismic links, we must have webs that are compact in shear. So the height of the web divided by thickness of the web must be lower than 72 epsilon. Full strength joints are recommended. Full strength means that we design joints with overstrength. We design joints on the resistance on the strength of the member that we are connecting, plus the overstrength that comes from the material. So the symbiotic connection and billet wells we must design on 1.1. This is the strength hardening part. Gamma overstrength takes into account the material overstrength and then the resistance of the element. All the connections must be designed in a way to limit the localization of plastic strains and residual stresses. The shear connections, the bearing strength, the shear resistance of the bolt must be at least 20% stronger than the bearing resistance all the bolts must be preloaded. The bolts must be 8.8, 10.9. Those bolts for preload. The friction surfaces A or B, and fitted bolts are also allowed. So now let's go to the moment resisting frames. How to design them? The global ductility. We want to achieve global favor with plastic yielding in the beams. So in the edges of the beams, at the base, and also here the columns can yield on the top floor. We must never allow soft stories, because this is not high ductility. The concept, big beams, strong columns. So that means that the sum of the plastic resistances of the cross sections of the columns in the joint. So this is the joints. Here we have the outer joint. So we have two cross sections of the columns and one cross section of the beam. So this of the columns must be at least 1.3 times plastic resistance of the beam stronger. So in this case we have two beams and two columns. So the columns must be stronger than the beams. This is the initial condition that we start with when we build our numerical model. This is the initial condition that we start when we choose the size of the column. What is the basic concept? The plastic hinges develop in the edges of the beams. So the beams are designed on the internal forces that come from our analysis, while the columns must be designed with overstrength. So this means that the forces that we get from our analysis, we must increase those forces with overstrength factors, and then we must use these forces to design the column. So how does this work? We do always a separate calculation So this is a seismic design situation or a seismic combination. And this seismic combination has non-seismic effects and seismic effects. And we must always calculate separately for non-seismic effects and seismic effects. So why is that? We will see here on this slide. So how we design beams? We design beams, so these are the dissipative zones. The bending should be lower than the plastic bending resistance. The axial force and the shear force must be limited to some very low, quite low values, because the plastic hinge must occur primarily due to bending, not to have influence of axial force and not to have influence of the shear forces. How we calculate the shear force? So the shear force is calculated as the shear force that comes from the gravity load. So this is the non-seismic effect for this part. And then from seismic load, the shear force is calculated on the assumption that plastic hinge occurs on both ends. So we have the bending diagram like this, and the shear diagram we calculate from this bending diagram. So the shear force from the seismicity part is plastic bending resistances divided by the length of the beam. So this is how we design beams. Of course, we must prevent lateral total buckling. We must support the areas near the plastic hinge, let's say by this fly brace or some other parts. We must have some stable length. So here is some lateral bracing, and this is the force that we design this support. This is also from the second generation of Eurocode. And what is important, that beam should not be made stronger as needed, because if we make stronger beams, this will put the higher demand on the connection and higher demand for the design of the column, as we will see now. So how we design columns? So first we must calculate the internal forces. So axial force, bending moment, shear force. This G letter means that this is the internal force that comes from non-seismic part of design combination, as shown here. So from gravity load and the live load multiplied by C2 factor. And then we add the part of internal force that comes from seismic effect, and we multiply this by 1.5 gamma overstrength, so this is the material overstrength, and omega. Omega is the overstrength of the element. And omega is calculated for every dissipative zone. So we calculate omega in the beams, on the edges of the beams when the plastic hinge occurs. We calculate it as the plastic bending resistance of the dissipative zone divided by the moment that it's in that area. So from the whole seismic combination. And we take the minimal value of omega, and put it here. So now we get the internal forces in the column that are increased. So this is the capacity design. So we increase the forces that come from the seismic effect, and we design column according to Eurocode 3 the way you know. An important part is also the column web panel. So the column web panel, this is the web panel here, so this is the beam, the column, and this is the column web panel, and this is not the shear force that is in the column. But the shear force that is in the column is like this, and from the bottom side like this, and from the analysis we get this line to here, and this line here, and here horizontal line. But we know that the bending moment cannot just jump from one value to another value. It must be connected. So in this column, there is high gradient of bending moment, and this high gradient of bending moment gives very high shear force in the column. In other words, the shear force in the column also comes from the beam, because on one side we are having tension, high tension, on the other high compression, and we are shearing this column web panel. So the Eurocode also gives guidance how to calculate this action on the column web panel, and this is the resistance of the column web panel that comes from Eurocode 3.18 from the design of connections. What is important that with this inner joint, the plastic hinge occurs here and the plastic hinge occurs here, and the bending moment are rotating in the same direction. So here we get plus. So the shear force in the column web panel of the inner joint is very high. It's 2 times plastic resistance of the beam divided by this level R Z. So this is a very high demand, and usually we need very strong columns, so we need additional reinforcement plate on the column web to transfer this high load. Let's go to the joints. So current Eurocode gives very little information on how to design joints. Only gives the resistance of the joint should be higher than the plastic resistance of the beam multiplied by overstrength factors. While the second generation gives much more information on this. It gives different design concepts. These are full strength, equal strength, or partial strength joints. But let's stay with full strength joints. We can see here these new factors, that material randomness and strain hardening. And then also this part, it takes into account the location of the plastic hinge. If the plastic hinge is located a little bit inside, away from the column flange, then we must take into account the bending moment caused by the shear force. So this is the shear force that comes from the seismic part. This is under the overstrength factors, and the shear force that comes from the gravity part. It's not multiplied with these overstrength factors. And these are the schemes of connection that Eurocode provides for the as some typical beam-to-column joints. So the first part, these two are unstiffened connections. These connections can only be used in dual frames or in moment frames with dog bone beam. So what is dog bone? Dog bone is when you cut the flanges to reduce the cross section, to make it weaker, so that the plastic hinge is enforced into this weakened part of the beam. While if you don't have this kind of connection, these stiffened connections might be used. So these are rib stiffeners, so we can have ribs on the bottom and on the lower part with 1 or 2 rows of bolts above the tension flange, or we can have a haunch, a short haunch in this bottom part. All these connections were pre-qualified. There was a large European project that they tested a lot of joints to show that these connections are really capable of staying in the elastic region when you develop full plastic hinge in the beam. And the Eurocode also gives guidance how to design the friction connections with friction dampers. When the seismic energy is dissipated in these friction dampers. So, I don't know, I'm a little bit long. I can stop here, or...
If you have 10 minutes.
Okay, we can go quickly through concentrically braced frames. Now the philosophy is very clear. So, we must design for dissipative zones. Here in the concentrically braced frames, the dissipative zones are tension diagonals, and all the other members must be designed with some overstrength. So the rules that we must expect is that if the diagonals are located in two separate bays. So one diagonal in two separate bays, then those diagonals must have more or less the same inclination. So this is checked by this cross-section, the projection of the cross-section of the vertical cross-section. So it tells us that one diagonal must not be very shallow and the other very steep. The frame is always designed on the gravity loading, while the diagonals are designed for the seismic loading. So the X diagonal, the dissipative member is tension diagonal, the V bracing, the dissipative member is actually the compression brace, and then in the end also this beam, we must design this beam to take the unbalanced load, as we will see on the next slide then. So the X bracing have a limit. If there is one or two stories, there is no limit for slenderness. While if there are more stories, there are two limits for slenderness. 1.3, this is the bottom limit, that the diagonals are not too strong because we could overload the current. And on the other hand, they must not be too slender, because if they are slender, they will go out of plane, and this is not very good when you have a big earthquake that diagonal goes into the space. If the diagonals are in two separate places, two separate bays, then it's only the upper limit for slenderness. X bracing we design for tension. In V bracing we design for compression brace, as we know it, buckling resistance. It's always recommended to have full strength connections. So how to dissipate energy? Of course, if you will use the same cross-section for all the bracing, then of course the bottom diagonal is the most loaded, and only the bottom diagonal will yield. So what we must do, we must decrease cross-section in each story so that the braces start to yield more or less at the same time. In this way, we will dissipate energy and achieve very high Q factors. So how to put it in numbers? We calculate this omega factor. In the moment resisting frames, we calculated omega based on the bending resistance, because the cross section was dissipating energy in bending. But here we are dissipating energy in tension force, so we are calculating omega as plastic resistance of the brace, cross-section of the brace, divided by the force in the seismic design situation. And the omegas that are calculated for each brace must not differ from more than 25%. So this will mean that we will have yielding more or less on all the diagonals will yield. And of course the diagonals must not be oversized, because this will increase the demands also for the columns and for the connections. So how to design the beams and the columns? The same story. If we design the column, let's say, we take the axial force that comes from the non-seismic part, so this is for the vertical forces, for the gravity load, plus C2 times live load, and add the axial force that comes from the seismic effect, and multiply this with overstrength of the material, and overstrength of the element is omega, the minimum omega from all diagonals. For V bracing, so the weakest point is this compression brace, and this compression brace will buckle, but when compression brace will buckle, this will cause some unbalanced forces on the beam. So we must calculate this unbalanced force So we say that when this diagonal buckles, it still carries 30% of load, and we get this unbalanced force that shows the arrow here, this arrow. And we must design this beam for this load and for the gravity load. And this is usually very high demand, and we get, if we have a span here, let's say 8 meters, we get such a high demand that we must use HEB 500 or very huge cross section that are not very feasible. So in these cases, other solutions should be applied. Why this unbalanced force? Because the tension diagonal must yield to dissipate energy. But of course, compression diagonal will buckle first. So there are some additional rules if we have diagonals in two separate bays. So we must design columns for not to be overloaded. But let's show the connections. So Eurocode, the second generation of Eurocode, gives many details on how to design the connection. So first he said, okay, you have to design here for a connection to have a hinge, so to have a rotation here, because this is very rigid. Then what is important is that we must have here some clearance that should be wide enough, so from 2 to 4 thicknesses of the gusset plate. And this clearance is important because the diagonal, as you saw, will buckle out of plane. And if it buckles out of plane, this gusset plate will bend. And when it bends, it yields. So if we have too narrow clearance, we will have very high plastic strain, concentration of this very high strain concentration, and fracture will occur very soon. So this should be sufficiently wide. It can also be an elliptical clearance. Sometimes it's easier to do it with elliptical clearance. Then we design this gusset plate for buckling resistance. So if this gusset plate is too large, then it can buckle, of course, under the load. And also we must design for tension resistance based on this Whitmore length that is shown here, WD. Some other kind of connections, these are knife connections. It's like this. In this case, the diagonal will buckle in plane. So these are the details that diagonal buckles in plane. Okay, because we are running out of time, I will go quickly through eccentrical braced frames. Basically, the rules are very similar. So we can have short links and long links or intermediate links. With short links, we dissipate energy in shear. With long links, we dissipate energy in bending, because if the link is long, then bending will prevail. Intermediate long links will dissipate energy in bending and in shear. So the seismic, the design resistance of the seismic link, so the bending resistance, we take into account only the flanges. And the shear resistance of the link, we take into account only the web. So the web dissipates energy in shear, and the flanges will dissipate energy in bending. The shear resistance checks if the axial force is below 50% of the resistance, so then the bending resistance must be lower than the bending action must be lower than the bending resistance, and similar for the shear. But what is the difference between short and long links? So we can have a simple derivation to have an analytical derivation, so that we will not go into details. So the length of the beam that is on the border between long and between shear and bending link is this 2 times inelastic divided by plastic resistance of the link. So the Eurocode gives criteria for links where the plastic hinge develops at both ends, so here and here, or where the plastic hinge develops at one end. So this is for where the link is positioned vertically. So you saw the analytical distinction between short and long link was 2 times this, but the Eurocode gives 1.6 for short links, and if it's larger than 3 times this, then it's a long link. For plastic hinge at one end, a little bit different criteria, and the resistance of the link if the axial force is higher than those 15%, we must take into account the effect of axial force that reduces the capacity of the plastic hinge. In these eccentric bracings, also the rotation of the link is limited. So we can calculate the rotation of the link from our analysis. We get this interstory displacement from our analysis. This is with reduced displacement. We must multiply this factor Q. Then we get the actual displacement, and we can calculate the rotation of the link via this formula that comes from this plastic mechanism. You can derive it quite easily. And this is the maximum value that depends on the length of the link. Eurocode also gives guidance on stiffeners, so the distances of the stiffeners, the thickness of the stiffeners. At the ends, there are always stiffeners on both sides. In the between, it's only one sided stiffener. For long links, the stiffeners do not need to be so dense. They can be more apart. But if the link is very long, so longer than this, then the stiffeners are not needed. Intermediate stiffeners are not needed. Again, we want to dissipate energy in all links at more or less at the same time. So we need to calculate this omega value. So this is the overstrength factor for the links, and the difference between maximum and minimum value needs to be lower than 1.25. This will guarantee us the dissipation, the yielding of the links at the same time in all the stories, and with this good dissipation of seismic energy. Omega value here is calculated a little bit differently. With short links, we calculate it from shear forces, of course, because it dissipated shear. While for intermediate and long links, we'll calculate it from the bending moments. And again, all the members that are outside the link, so this means the braces, the columns, and the beams up to the link, we must increase the forces with these capacity design rules. Because axial force is dominant, we only increase axial forces, so we take the axial force that comes from this non-seismic part of the seismic design situation, and we take this axial force that comes from seismic effect, and we multiply it with overstrength factor from material and from the element material overstrength. The joints need to be full strength again. And again, the current Eurocode does not give any guidance on how to design joints. Only gives this equation. So, okay, you design joints full strength, take into account the element overstrength and the material overstrength, but no details. But the new Eurocode also gives some details how to design these joints. So you can see here one welded connection. So this is the seismic link. The braces are welded, so and we can also connect the brace to the gusset plate. So what is special here that this gusset plate has stiffeners on these sides to prevent bucking of the gusset plate, or a bolted version. So gusset plate with stiffeners and everything is bolted on the beam. Okay, this is everything for today. I was a little bit long. I apologize for that. The topic is really wide, and we covered only the fraction of it. Thank you very much. So, are there any questions?
We will ask the audience if there's some questions for you.
Thank you for the presentation. We covered different systems for dissipating energy, and there is one system that is barely mentioned in any code, but that the architects, some architects really love to use, and that's the diagram system. Do you have any knowledge or guidance on how to deal with those in the seismically active regions? There are some studies, but they are not so official in the codes.
What kind of system is a diagonal?
Diagonal system. It's a system where diagonals carry gravity loads as well as dissipate the lateral system. There are no verticals in it. There are only diagonals, and yeah.
No, there are no information on Eurocode how to deal with that. So for this, some more advanced analysis should be done, at least pushover analysis. But yeah.
Pushover analysis to prove what is the ductility of the system?
Yes, to show where to dissipate energy, how to if it has sufficient ductility.
Because the dilemma is whether it can be plastic at all. It has to remain elastic to take gravity loads.
Yes, because once in those systems you don't have columns, once you dissipate energy in diagonals, then it collapses. It needs to be statically indeterminate in a way to prevent the collapse. But Eurocode does not give any information on that.
How about the steel-plated shear walls, and specifically composite steel-plated shear walls? Are there any improvements in the latest version of the Eurocode?
Yes, there is a special chapter on shear walls. On steel shear walls, I know, and I think also on the composite shear walls. So there were some European projects on that, and it's also included in the second generation of Eurocode. This is also one of very effective systems. It's very stiff and with the ability to dissipate. What are the current trends is they are going in a way to the main. Now we saw more or less how to dissipate energy, and the structure will remain, will not collapse. But the problem is when you have a major earthquake, that the building can be placed out of vertical, and in this case it's difficult to repair such building because you cannot pull it back. So many studies or many research is done now how to make these self-aligning systems or self-centric systems, and they have some they figure out some quite simple systems and very effective systems where you can store elastic energy in some way, and this elastic energy is then used to put the building back into the vertical.
Maybe a related question. First of all, thank you very much for a very detailed overview of both existing and the new Eurocode, and lots of very useful information. So I'm wondering, what is your opinion on those systems that would, let's say, within the conventional steel structures without energy dissipation systems, if you put it as a separate chapter, a separate topic, which of these systems that you discussed and are currently in the Eurocode you consider as the best in terms of the minimizing damage and possibility for replacement after an earthquake, and what you mentioned also, these residual deformations which we don't like to see, because if you start talking about frames with the hinges, and we know what happens with the hinges and all that.
Yeah.
So what is your opinion personally as a designer and as a, of course, professor, but from a practical point of view?
Yes, these systems, self-centric systems, have very expensive details, and it's also quite difficult to control them. But one of the systems that was tested, I actually it was here in the beginning. It's a very simple system and a very good idea that actually worked. But it was this one. So here, this is the centric bracing. This is the moment resisting frames in this way, and in this way is moment resisting frame. And here, this is the link that is attached, and it's possible to change it. So what is the idea? The moment resisting frame it's not that stiff. It's very flexible, and all the energy, the seismic energy, will be dissipated in these seismic links, while the moment resisting frame will stay in elastic region. So when the building is tilted, you can take these seismic links out. You cut the bolts cannot be unscrewed. You need to cut them. They cut the bolts. They pull this out. And the elastic energy that was stored in these moment resisting frames put building back into the vertical, and then they replace the new links. So this is one of the possibilities that it's very easy. But of course, here you see there are no partition walls, no equipment in the building. It's a question whether this would also work in such real building. And also, what you asked, the systems, so this the friction connection that I showed, where you dissipate energy with friction, this can be combined with some systems that have the ability of self-centering. So there is no damage in such systems where you dissipate energy with friction, and in combination with some systems with the ability to self-center, it's very promising systems to overcome these disabilities that we have now.
And they're in the framework of the new Eurocode?
Those self-centered systems, not yet. No. But the friction connection, yes.
Thank you.
First time, thank you very much for the presentation. The question is really for the pre-qualified connections. Are they patented like in the States? Because after Northridge they used to patent those connections, or are they free to use?
They are free to use. You can download the old publications in the ECCA website. I think it's stillconstruct.com, something like that. And there are the publications in many European languages with the guidance how to design them. So these are basically, they're very similar to the connections that we use, but there are all the details on the welding, how to weld, how to strengthen the web column, and so on. So this is all free and available. But these friction connections, those friction pads, and the material that is used, this is under patented, and we don't know actually what material is that.
Thank you. Thanks. So thank you again for taking your time and giving us this lecture, and I hope to see you again.
Thank you for your kind invitation.